Hello guys, welcome to my channel. Today we're gonna discuss the solution of the problem B of the Codeforces round 930. Let's see how the problem looks like. Okay, here's the statement. We're given a 2x(n) grid filled with zeros and ones. Let the number at the intersection of the ith row and the jth column be a sub ij. There is a grasshopper at the top left cell 1,1 that can only jump one cell right or downwards. It is an important part of the statement. You can only move right or downward. It wants to reach the bottom right cell 2, n. Consider the binary string of length n+1 consisting of numbers written in cells of the path without changing their order. Your goal is to find the lexicographically smallest string you can attain by choosing any available path, and find the number of paths that yield this lexicographically smallest string. Here they give you a definition of a lexicographically smaller string compared to another string. It says that if two strings S and T have the same length, and then S is lexicographically smaller than T, if and only if, in the first position where S and T differ, the string S has a smaller element than the corresponding element in T. This definition is very important in the solution of this problem. Well, the constraint of n is this one. N is greater than or equal to 2 and less than or equal to 2 multiplied by 10 to the power of 5. They give you two strings consisting of the binary strings of the grid, the first and second row, and they give you this restraint that the sum of n over this case doesn't exceed 2 multiplied by 10 to the power of 5. Then we have to output the lexicographically smaller string you can attain by choosing any available path and the number of paths that holds that condition. So now let's analyze how we can solve the problem. This is an example of a grid. It is this case. I put that on a PDF. So the first observation that we have to make is that, okay, we start in this position and we're gonna go to either to the right or down, either to the right, and sometimes maybe we could go down and then to the right. An important observation is that once that you go downward, you cannot go upward or to the left. The only thing you can do is to steal to the right till the end. It seems a very straightforward thing to notice, but it's very important to the solution of the problem. Once you have gone down, you can only do this. Go from this position to the last position of the second row of the grid. Then taking advantage of this thing, okay, that's it. Taking advantage of the definition of here, that you have two strings of equal length. The smaller lexicographically is okay, we're gonna compare the two strings. If you have two strings of the same length, you're gonna start comparing them from left to right, and in the first position that they differ, the smaller string of those two strings is the one that has the smaller character. So now suppose, okay, we start in this position and we want to make the path, the string that will be formed by the path, whatever string it is, but we want to minimize this string lexicographically. Now the string starts with the number may be either of 1 or 0 that is in the cell, in the initial cells, which is 1, 1. So in this case, the first position of the string is 0. Now the second position is determined by either two options. I can go to the right or I can go down, but not both. If I go to the right, the second position will be 0. But if I had gone downward instead of to the right, the second position will be 1. So you can see that this string will be it's already smaller than this one, because this position has the same character, but in this position 0 is less than 1. So this string will be better. So well, what we have seen so far is that, well, whenever you are at some position of the grid in the first row, if the cell that is to your right is 0 and the one that is down to you is 1, it is better to go to the right. So that's an important thing. Suppose you are at some position, here you have a 0 and here you have a 1, so in this case you're gonna go to the 0 position. Now we want to analyze all the cases and see what is beneficial. So if we are at some position and let's say that we have both 1 here and 1 here, an important thing to observe here is that we can always, if I go to the right, I can, well, let's see it in another way. If we have this x, we are in some position. To the right we have a 1 and downward we have a 1. If you go downward, looking at the first observation that we make, that says that once you go downward you can only go to the right, and so the string will be determined. If you go downward, then you can only go to the right. But if you do that in the case in which you have 2 1s, you can also go to the right and go down, and you'll have the same string. So in this case I have demonstrated that in the case that you are at some position, okay, you are at some position in the grid in the first row, and at your right you have a 1 and down you have a 1, you can always go to the right, and the string, the solution, the string you are looking for, will not get worse. Okay, so in this case we can go to the right. Now the other two cases are in which you are at some position in the first row, you have a 0 at your right, you have a 0 downward, and in this case, using the same argument that we use here, if you go down here, so you will have to go to the right, you can always do that going to the right here, then going down, then going to the right. So the solution doesn't work if I go to the right. So the other case is in which we are at some position at the right, we have, okay, here a 0 and here a 1. It is the leftover case. So in this case, based on the observation that we always want to minimize the character that is in a position, the beneficial will be to go downward looking for the 0, and after doing that you are gonna, the string is already determined, going to the right in the second row. So that's all the possibilities. So what we have seen so far, like in order to construct the string we are looking for, we can start here, and based on these 4 cases we can move to the right or downward based on these two 4 conditions. Okay, let's simulate this case to see what the solution is. Here I have to my right a 0 and downward a 1, where in this case we can move to the right. Okay, here we have 1 and 1, where in this case we can move to the right. Now we have a 0 to the right and 1 downward. It is, see, okay, this is this case, and we can move to the right. Now we have 2 zeros, we can move also to the right. 2 ones to the right, 2 ones to the right, but now, and in this position we have a 1 to the right to us and a 0 downward. So we are in the fourth case, that we have already demonstrated that the optimal step is going downward. So we must go downward, and then we are forced to finish to the right until this one. Okay, this string must satisfy the condition that is the lexicographically smaller string that can be formed by traversing the grid, with the condition that you can only move to the right or downward. So we have based on this fourth condition an algorithm to finding the smaller string that can be formed. But now we have to find the number of ways this string can be formed. We can check that this string coincides with the solution of this case. Now let's delete. Okay, this is not, let's delete all the stuff. Now, how we can find the number of different paths that give us the given string? So the string was okay, wait a minute. That's it. This is the string. I'm gonna write it down. We have a string 0 0 0 1 0 0 1 1 0 1. Let me check. 0 0 1 0 0 1 1 0 1. Okay, this is the string that this is the solution. Now we have to find the number of ways we can form that string. Okay, let's analyze. This part is pretty similar to the past part in which we find this string. We found this string. We're gonna start again from the initial position, going to the right or downward, respectively. We have to see that the only position in which I'm obligated to go downward, whether, okay, I'm in some position on the first row. The only case in which I am forced to go downward is in the case in which I have a 0 down below me and 1 to the right. So we can go start from this part, and whenever we are not forced, I mean in every case other than this case, we know that it will be that going to the right will not worsen the solution. So we want to analyze if, okay, what happens if I haven't gone to the right? If I haven't gone to the right, so I had to go downward. And once you go downward, we have already demonstrated that the only thing to do is to go to the right till the end. So in every position in which I'm not forced to go downward, I'm gonna analyze, okay, if I had gone downward, that string still satisfy that is minimal. But so in every step we do that. But in order to compare, suppose we have done that. In this case, I wanna try, okay, if I had, okay, in this case, no, in this case, in which I have 0 and 0, I can go down and then to the right. Now I have to test if this substring here is equal to the corresponding substring of the solution. 1, 2, 3, 4, 5 cells, 1, 2, 3, 4, 5. I want to check if those strings are equal. Well, they are equal. But I want to do that in every step. In every step, I check. Okay, if I go down, then is this suffix. Okay, in every step in which I can go to the right or down, I'm gonna ask, okay, here, if I go down, is this suffix equal to the corresponding suffix of the solution? If yes, it is a possible solution. If no, it isn't. But how can we do every time that we analyze the case in which we go downward? How can we how can we compare this suffix to the corresponding suffix of the solution in a fast way? Well, if we do it naively, the solution will have a complexity of n squared, and it will give time limit exceeded. So the thing is, we need to pre-calculate which suffixes matches the corresponding suffixes of the solution. It can be done in linear time, going from the end to the beginning, and just well, what I did in the implementation is I had an array of booleans started from the end, and if they are equal, I put it as true. Till they are equal, I put it as true. In the first position that they differ from backward, I marked it as false, and all of these till the first position false. So I'm gonna run the algorithm, and whether I can, in the position that whether I can go to the right or down, I'm gonna say, okay, if I go down, is this substring, is this suffix equal to the corresponding suffix of the solution? And that can be checked in O of 1 using this array. If it is false, it isn't equal, and if it is true, it is. So in this way we solve the problem in linear time. Now let's check my code solving the problem. I copy it here. Come on, you can hurry up. Okay, let's see. This part, the other for this one. Well, here I'm reading just the input, the two strings. I put it an asterisk before each one because I like to work with the string from the position 1. And this string is the solution string. I did the same to this string, and I added the first position because this position is determined. I have no choice. Now, okay, in this loop, it is the first part of finding the solution, the string that yields the conditions. in this string, and okay, this is the case in which I am forced to move downward, because for example it was here. When I was here, I have to move downward because there is a 0 downward and a 1 to the right. So in this case, in which there is a 0 downward and a 1 to the right, I add this 0 to the position, to the string, to the solution string, and I go from the next position in the second row till the n-1 position. In this case it coincides, and at the end I added the last position. Okay, and then I break. If not else, I just add the cell that is right there to the current position. The vector mark is the vector I told you before, where mark in I is true if and only if the suffix of the string s2 starting from I is equal to the suffix of string s3 starting from I plus 1. Here is where I do that. I initialize pos in n while pos is greater or equal to 1, and this holds, mark is true. If it doesn't hold, so I go out of the while. Now this part here, this cycle, it's a little bigger, a little bit. It's for counting the number of solutions. So I start from the position 2 to n. This case is where the suffix of s2 starting from I-1 matches the corresponding suffix of s3. In this case is in the cases in which I can go down and the solution yields. So I sum 1 to n's. Now this case here is in the case in which I cannot move to the right. For example, this one, I cannot move to the right because here there is a 0 and here there is a number 1. So I am forced to go downward. And in the case, if it case holds some time, it will either it happened or already. So I have not to sum any to ones because I have already summed this here. And what I put here, if no flag, so if I didn't enter here, I have to sum 1 to ones because I didn't count the straightforward solution that was going all here, getting just down here. Okay, I print the string and print answer. That's pretty much my solution. I hope you have enjoyed the video and it would be helpful to you.